whenever you're ready, take it away.
All right.
Are Jim's slides yours too?
Yeah.
He's not here.
I'm just gonna go through this one. All right, guys, we are group number 5, and we're presenting in situ air stripping technologies. In situ air stripping is a pretty simple concept. Basically, you just pass air through contaminated groundwater with the hopes that the contaminants will evaporate out into the air from the groundwater and can therefore be removed. Obviously, when doing this type of work, you have to be mindful of what type of contaminants you're using or are present. VOCs and other compounds such as TCE with high vapor pressures are the ones that can be used with this type of method. Heavier contaminants that don't easily evaporate out, such as oils or anything like that, will not be able to be used with this type of system because they won't evaporate out, and therefore it'll render the system ineffective. So there's basically 3 different types of air strippers. There is the low profile sieve tray system, the packed column system, and then a diffused air stripper, which in the diffused air system is not very commonly used. It's used for only specific scenarios, so we'll go over that later. Low profile or sieve tray system is a fairly common system that operates using sieve trays that have little holes in them. Basically the water runs over the top of the sieve tray and air bubbles up through those little holes through the water and then removes the contaminants, and then is then passed out through the top. So you can see here that the water will run across these sieve trays, air will bubble up through the top and out, and then the treated water will be down at the bottom. And then the next type is a packed column system. This system uses a large column filled with packing material. So the water is brought in from the top and trickles down through the packing material. The goal of the packing material is to actually distribute the water appropriately, so it's not, all the water going down one side or the other. This allows for more surface contact between the air and the water, and an overall more even and efficient contaminant removal. This system uses a concurrent flow, so you have air coming in this way versus water coming down this way. Then the contact of the air with the water removes the VOCs, and they exit out the top while the treated water comes out the bottom. The third type is a diffused air system. Like I said, this is basically just a water tank that has little nozzles at the bottom bubbling air up through it. This system is not as efficient due to the fact that there is just less surface area for the water and air to contact with, and therefore less efficient removal of VOCs or whatever contaminant you're using. But the advantages of this system are it's a very simple and durable system. So if you have a groundwater that has a lot of dissolved solids, you expect a lot of corrosion. This system is very easily cleaned and very easy to deal with. So the advantages of this is it's not susceptible to fouling or anything like that, but it's not nearly as efficient as the other 2 systems. So generally it's only used for those specific types of groundwaters that have high dissolved solids and you expect a lot of fouling. And then a comparison of a low profile sieve tray versus a packed column. The packed column is more popular simply because it's a much larger system. You can process a lot more wastewater, and it's also a little bit cheaper than a low profile sieve tray. However, both systems are able to remove over 99% of VOCs, so they're both very effective systems. Packed column strippers also require less air to treat the same amount of water than your low profile systems. So if you're concerned with actual treating of the air containing the VOCs, where you're not able to, where environmental regulations don't allow you to vent the air straight into the environment, the packed column would be the way to go because you have less air to treat in the end. Packed column can also operate over a much wider range of airflows than can the low profile sieve. So if you have if the water flow drops significantly, a packed column can compensate for that and also drop the airflow. Whereas a low profile sieve cannot drop the airflow as much, so you could run into issues with that if the water flow drops too much. However, one disadvantage of the packed column is it's very susceptible to fouling due to the packing materials and the tighter spaces. So you need a water that's going to be able to foam easily and not foul very much, because they're also very difficult to clean once fouling occurs. And a low profile sieve system, one advantage is that it's much smaller and sleeker. Obviously you can see this is a packed column. It's a very large, kind of bulky unit. So if you're in an area where height restrictions are an issue, or you're not able to move such a large unit, a low profile sieve may be the way to go. They're also easier to clean, so if you have groundwater where a little bit of fouling is expected, not a whole lot, You can use a low profile sieve still because they're very easy to clean and they're not as susceptible to fouling. However, they're typically a little more expensive, like I said, so generally people will go with a packed column unless the parameters do not permit a packed column to be used. And Eric? Yep.
So I will introduce some of the important parameters in the strippers design. So the basic idea for strippers is absorption. We learned from ENVSE 427 and EGE 470. The most important thing is the air's volatilization from the water, which means that when the air flow above the water surface, the gas VOCs in the water will become gas and go with the gas, from the bottom to the top. Some of the parameters are the gas pressure drops, mass transfer coefficient, packed materials in the whole machine, and the air to liquid flow ratio, column height, column diameter, and contaminant concentration, and expected effluent concentration, and Hohenstahl constant, which means that the ability for the VOC to vaporize from the water to gas. So in general ideas, the higher the stripper and the higher the air to water ratio, we will have a higher removal rate of the contaminant. Because when we have a pretty large air to water ratio, the gas flow rate will be pretty high. When the water surface is under a pretty high gas flow rate, the VOC have a better potential to become a gas phase. So, because we need to think about the economics, when we have a higher column and a wider diameter, we will need to spend a lot of money on that. So we want to minimize the column height. Here is the equations determining the column height. L is the liquid loading rate. Because the stripper is a process of the pump and treat, so it will be basically determined by how much we want to treat for each day or each year. And KLA is a mass transfer coefficient. R is a stripper factor, I will talk later. And C out is the expected contaminant concentration in the liquid. And diameter is simply decided by the liquid flow rate. So here is the stripper factor. On the top is the operating gas to liquid flow rate, and on the bottom is the theoretical minimum gas to liquid flow rate. It will basically determined by the Hohenstahl's constant. The higher the Hohenstahl constant is, the lower the gas to liquid flow ratio we need, since that the gas has a pretty high possibility to vaporize. So we don't have to blow so much gas. And then is the mass transfer rate. This one is basically related with the packed material, because there are many different kind of packed material in the packed column, such as the sheet rings, burr saddles, and tile. And you can see there is an alpha and N which will help us determine the KLA. So as you can see in this one, determining the column height, we want higher KLA value to minimize the height. So we will be choosing from this packing materials to minimize the height. And also the packing material will be related with the gas pressure drops, which means that this one is the resistance, the aeration machine from the bottom need to overcome. So we want the gas pressure drop to be smaller, to be smallest as possible. And this will be a function of gas flow rate, water flow rate, and packing size and type. We will have a pressure drop curve that will help us to determining the gas flow rate from the certain pressure drop, because that one is related with the aeration machine's power. There are several designing procedures. First, we want to select a packing material which has a higher KLA and lower pressure drop, and then select a air to water ratio that will help us determining the stripper factor R, and then calculate the air flow rate based on the gas pressure drop curve. And since we have the operating gas to liquid flow ratio, we can have the liquid loading, and then we use the we have the height equation and the diameter equation help us to determine the size of the column. So in conclusion, that these are the physical factors affecting the stripper effect, stripper's performance. The most important is the contaminant Hermit's loss constant, and then also liquid density, viscosity, diffusion coefficient will help us to determining the mass transfer rate, and the target effluent concentration, and affordable gas to liquid ratio determined by the aeration machine's power, and packing material, and yeah, that's it.
And so I will be focusing on the influencing factors in the maintenance of in-situ stripping. The average turn duration typically requires 3 to 5 years to remediate a site, and the duration of operation and maintenance is dependent on the following conditions. The first one is cleanup goals. The second one is the aquifer characteristics. The third one is biodegradation, and the last one is system optimization. So for cleanup goals, in order to do so, we need to identify opportunities for modifying cleanup goals based on regulatory changes or updated contaminants, toxicity information. And for the second one, utilize groundwater monitoring data or develop site-specific groundwater transport models to help negotiate cleanup levels of residual contamination at the site do not pose a threat to potential receptors. And next, we have to identify sites where engineering and institutional controls can be used to reduce receptor exposure to contaminate soil or groundwater. For example, the cleanup requirements can be reduced with the use of appropriate data instructions, which establish the site as a brownfield, limit future land use, and grant future residential development. These options must be discussed with the legal counsel, and the long-term use of the site should be considered. Land use controls may not always be feasible and federally on these sites, and I have attached the figure of a conceptual site model based on the time series plot and total VOCs concentrations, aiming to have a better and healthier in-situ stripping process. And the second one is the aquifer characteristics. When air sparging encounters low permeability and semi-confining strata, sometimes can bring challenges to operator. For instance, if the contaminants of concern are located beneath a semi-confined unit, air bubbling into this unit could become trapped or travel horizontally, potentially facilitating migration of COCS. If COCS are located above and below low permeable stratum, it may be necessary to install nested sponge points that are dedicated to treat both steps intervals. And the next one is focusing on the biodegradation rates. And this table lists the contaminants that is successfully removed via air streaming process. In general, for this process to be effective, contaminants must be neither sufficiently volatile to strip out the groundwater, and last but not least, aerobatically biodegradable. In order to enhance the biorejuvenation, one can increase groundwater dissolved oxygen concentration, and for the sites that already has DO concentration greater than 2 micrograms per liter, then the system may not be warranted. Here's a schematic of a combination of factors. And this is a basic flow chart that serves as an initial screen methodology for determining if the air stripping system is appropriate for a given site. And the last one is system optimization. And some points that stand out we need to take into consideration. The first one is focus strategy, sparging well placements. One can run on localized area with elevated contaminants concentration. This approach can greatly reduce the cost of the installation without substantially increase the operation time. The second point is about the reduction of the design capacity of air supply, vapor extraction, and vapor treatment units. This approach will result in a system that operates near its optimum design capacity for a longer duration. And the last perspective is to consider the constructing air supply, vapor extraction, and treatment units on a mobile trailers. This approach has been used at many installations to reduce the fixed cost of equipment and enable the equipment to be reused at other sites on the installations. Furthermore, the air supply and extraction equipment can be employed for multiple uses. Typically, these equipment items can be considered to have served lives of approximately 5 years, depending on the site quality and the relevance.
I'm going to go over how these mechanisms are implemented into the field, and then as I go along, Justin's going to speak to some of the applications and limitations of these specific techniques. Admittedly, as we go down, I think the definition of air stripping gets a little bit more broad, but they still follow the same principles that air stripping remediation sites would have in the field. So to start, we have kind of like the most basic one, and that's just in-well air stripping. So pressurized air is injected through a vertical well that's been screened at 2 depths, and the lower screen is submerged in the groundwater, so it's in the saturated zone, while the upper screen is in the vadose zone. And as the air goes down into and exits the bottom screen, the groundwater is going to get drawn into the well, and as it goes back up, the groundwater is going to be aerated, and that's going to extract and volatilize those VOCs, or vaporize those VOCs, sorry. Once it gets up to the upper screen, that contaminated water is immediately injected right back into the saturated zone, while the VOCs rise up to be extracted by soil vapor extraction systems, and I'll refer to them as biovents throughout this too. But when that partially treated water is re-injected back into the saturated zone, it creates this kind of circulating well effect, and I'll talk about that in a second too. But the duration of these remediation techniques are pretty short to long term. and it really depends on contaminant concentrations, Henry law constants of those contaminants, the size of the plume, and then site hydrology. And that's a lot of what Eric was speaking to earlier. So the circulating well is good because it reduces pumping costs, so you don't have to bring the water up to the surface, hence the in situ part. And that's really good as far as permitting and having to deal with contaminated water at the surface and discharge of it. And with the circulating well, you could also simultaneously treat the vadose with those soil vapor extraction systems. So here's a picture of that in-well air stripping. Up here you have your upper screens, and down here are the lower screens. So the pressurized air is going to come down, bring that water in up through the well. Right here, it's like W double arrows right here. That's where the VOCs are going to rise up to the top and then go to those packed columns. Here it's a blower and an activated carbon filter, but essentially this is the soil vapor extraction system. The water, while the VOCs go up, is going to be injected right back in, getting that circular well effect. This is a similar picture, a little more rough around the edges, but you can see a few other things a little better. So you can add chemical additives to help with biodegradation of those contaminants in the water. And they're going to come out at this upper screen and go right into the top of the water table and get caught in that circulating well. Additionally, chemical additives could be added to the surrounding area, which may be affected by the circulating well effect. And that will just help stabilize metals that may be found in groundwater anyway. Again, those VOCs are going to rise up and then get extracted out with the SVE or the BioVen, and then get removed to be so that air can be treated. Otherwise, it's contaminated air essentially leaving this, so it definitely needs to get treated.
So now we're going to look into what different contaminants can be remediated using this technique. As he briefly mentioned before, VOCs are going to be one of the big ones, and semi-volatile VOCs, and also some fuels as well. When using this thing, it is better to use with a deep water table because it doesn't have to be brought to the surface, as he spoke on before. So that makes things a little better when we have a deep water table. Also, when we're dealing with sites with really high concentrations of these dissolved contaminants, because these high concentrations also usually bring a high Henry Law's constant that Eric spoke on a little earlier too. But when you've got to think of the limitations of this thing, it is very limited to when you're dealing with shallow aquifers. And moreover, you got to also consider the precipitation of the area that you're working with, because with precipitation there is tendencies for high infiltration, and when water from the surface infiltrates, you run the risk of having different oxidants come in that can plug up your system. Also, you should be aware when you're looking into your system, make sure that there's no inapples present, because when going through the system, the inapples can make a smear that will contaminate the vadose zone further. Also, some other things, you got to look at the soil. You've got to make sure the hydraulic conductivity is greater than 10 to the negative 5 centimeters per second. And you also got to look at the other components of the whole geology of the hydrogeology of the area, and make sure there's no strong natural flow patterns going on as well.
Our next technique is air sparging, and this is pretty similar to as far as implementation, to the in-well air stripping. But with this one, it's going to rely a lot more on the volatilization of those VOCs. Vaporization. All right. Because with this one, you're not going to get the circulating well effect as much. It's going to be primarily horizontal and vertical channels in the subsurface that's going to create the flow. And these air bubbles are going to push the contaminants up to the unsaturated zone. And that's where you're going to get the stripping effect. So it's going to act as an underground stripper, and it's going to rely less on the actual in-well stripping. This will be coupled again with the BioVen to remove those vapor phase contaminants from the vadose zone. And that'll be through the collection channels, kind of not as deep as the injection well, but just into the vadose zone. The addition of oxygen will help with biodegradation of these contaminants, and this is a longer one of the methods that we'll talk about, taking up to a few years. So here's a picture. This well on the right is not in situ, so we can ignore that. But the air is going to be injected, and this is going to rely on a high flow rate to keep these bubbles moving up to the top of the water table, where the contaminants will get carried up and then stuck into the vadostone. And then these collection channels from the SVE are going to bring them up and carry them onto air treatment. Yeah, again, high flow rate, just to keep that stripping effect going, because it's not happening in the well in this one.
So similar to in situ air stripping, the air sparging, there's going to be, obviously, because it deals with volatilization, VOCs are going to be the targeted group as well as some fuels. Now this process can be expanded out to tackle more sophisticated things like chlorinated organics if you add an methane amendment. Some limitations to this one that you don't see as much with the previous technique is because the airflow is moving through the soil and geology of the ground, the airflow is not going to be too uniform, and this can cause for some variability of where the contaminated vapors are going to land. So, for instance, the depth of the soil heterogeneity can cause some of the areas to almost pocket some of these contaminants, and other places not even hit the area that's affected with it. So you got to really look into the hydrogeology and geology and soil characteristics of the area when dealing with air sparging.
All right, bioslurping. This is my favorite word that I learned doing this. But this is the application of vacuum-enhanced dewatering technologies to treat hydrocarbon-contaminated sites. So this is the first one we're looking at that could deal with LNAPLs. It uses a combination of bioventing and free product recovery, so you're actually able to target two different phases of contaminants with this one. It's high efficiency in terms of collecting a lot of free product while minimizing the water extraction. And the vacuum-enhanced pumping allows LNAPLs to be lifted off of the water table and reduces off the water table and from the capillary fringe, and that will reduce the amount of, again, water getting extracted, and that's going to minimize smear zones. So, yeah, very in situ in terms of no water is really getting collected up in this method. Soil gas is extracted via recovery wells. Again, that's those biovents, and while the soil gas is extracted, that's going to leave room for air to get drawn in. So the bioslurper will actually be able to be converted to a biovent relatively easily once it's done its job. And this is like a median range of treatment as far as the technologies we're going over, ranging from a few months to a few years. So this air-liquid separation box up here, this is the bioslurper, and that's what's going to draw in the LNAPLs. And once those are withdrawn, bring in the soil gas, this is what's easily converted to the biovent to treat the VOCs that may be present there. I don't think the injection well is present, but that's where you're getting these horizontal flow lines and the pressure-induced flow lines. And yeah, I think you kind of get the pattern now. It's going to go up. You have your treatment methods up top, but no water is getting removed and no dirt's having to get dug up. It's just most of the contaminants getting drawn out.
So this technology is actually pretty cool because unlike the previous ones, we dealt with pumping air into the ground, and this one's more sucking the contaminant out, so it's kind of a little different. It is the most cost-effective method for removing LNAPLs and oil hydrocarbons. Also, it is really effective at deep water tables, as the other one was before, greater than 10 meters. However, when you're looking at the limitations of this technology, it isn't very effective at low permeabilities. So this kind of makes sense because the tighter packed the soil is, the less ability for the system to suck out any of the LNAPLs. Also, you got to watch out that the soil isn't too dry to begin with because this technology does tend to dry out the soil moisture. And also, when you're dealing with this, you got to consider the time of the year you're working with it because at low temperatures, the system does become less effective. But it is pretty useful because it does the ability to have
take out air and fuel at the same time rather than pumping air in and putting it all into one phase. In the gas phase, this you can do multi-phase.
Thermal treatment's a little different because it doesn't rely as much on that air stripping effect, but it follows a lot of the same principles still. So steam is forced into those injection wells, and that's going to, or hot water, and that's going to vaporize any semi-volatile organic compounds in there. And it's especially used when you have large plumes of oil in a groundwater system. It's also helpful to slow down the downward flow of those contaminants because it really focuses on containing them back into the specific localized plume instead of it being dispersed throughout the groundwater system. These are some of the systems. On the next page, we're going to be looking at the CROW system, Contained Recovery of Oily Waste. But this is a pretty short-term treatment method, and you'll see why in a second. But yeah, here we go. So again, I think you get the pattern. Steam's injected down, and this is why it's kind of short-term. It's pushing all of the oil here, but the contaminant into this towards its original plume where the production well is, and that will be able to bring up the contaminant to be treated. I don't think there's anything else too new on this picture though.
So some of the applications for thermal treatment is similar to what we've been dealing with before. It targets semi-volatile VOCs and fuels, as we saw in the previous slide. It is useful, and it is because it is a bit more cost effective compared to other technologies. It has especially in the United States, there's a lot of plants in areas like with the previous one he spoke upon there was a gas well or an oil well. So you can put that in already retrofitted or already fitted gas plants, as long as other places that have similar fuels and VOCs being leaked out, like wood treatment facilities and petroleum refining facilities. But as with pretty much all the other technologies, the effectiveness is based on the specifics to the site, like the soil type, the concentration of the contamination, and the hydrogeology of this subsurface.
So directional wells are more of an aid to enhance the other in situ technologies that we already went over. And this is used when you can't drill straight down to treat the contamination, whether it be, like it may be because there's a fracture that's not contaminated, and if you break that fracture, you're going to enlarge the contamination range. So drilling techniques are used to position the wells horizontally or on an angle to avoid these fractures that may be present. There's a bunch of hardware which is kind of pretty technical, but I just want to note that these thrusting machines have to be able to thrust with 40 tons of force in order to bore through the subsurface. Directional control is obtained by properly positioning the well at the start and then pushing it down. But as you go down, a slow rotation of the boring head is going to compact the soil into the bore walls and move it down, while not rotating that boring head is going to, you kind of picture it in your head, but if you don't rotate it, that's what's going to cause the directional change as you go down at the specific height you want it at. So here's a pretty basic picture of I mean, they can go angle too, but directly horizontal wells. And the machinery is capable of initiating the borehole up top, digging down to your desired elevation, and then turning laterally to continue on that horizontal well path. And then eventually it will go downrange and resurface.
Now with this technology, as he spoke before, it is good for being able to avoid certain things in the subsurface that you don't want to interact with, but this also can be extended out to the things on the surface. So for instance, in an area where you can't draw a vertical well, for instance, if there's a building or some kind of structure or landmark that you don't want to disturb, this is good because you can draw underneath it and at an angle on within the subsurface. That makes it pretty useful, but you do have to consider the drawbacks of that. One of the limitations is that there is a large potential for wells to collapse, and along with that, requires a lot more specialized and expensive equipment that a lot of companies don't have. So it's kind of more of a specialized technique. And as he said before, there's a lot of energy needed for these for these drill heads to make it through. So the precise location of the drilling path, I guess you would say, is hard to obtain, especially because of all like the factors that go in with it. And lastly, as you can imagine, because of the specialized nature of this technique, it is very expensive, and the depths that it can drill at is pretty limited as well, which not being much deeper than 15 meters. So after getting all that stuff out of the way, I think we kind of want to have a recap on some of the equipment, because after this we'll be talking about some case studies. So as we go along in this brief recap of equipment, I think it's good to keep in mind when you're looking at these case studies why they chose this equipment and what other things influenced the reasons for the case studies to be the way they were. So as Keith mentioned earlier, we have the packed tower air stripper. It is very effective, most commonly used, and it eliminates a wide variety of VOCs. Since Keith already went through how they work, we won't go too in depth on this. But basically, as it goes, there's the packing within a column can be a big factor. So if you look here at the multiple sieve tray style, it's much smaller, much more compact. With the size of the packed air tower, as you can see for perspective, this is a house right here. So this thing is easily going over 2 to 3 stories high. So when you look at these things, these systems can range from something, this is probably mid-scale. I see things that were much larger than this, probably the size of 2 sedans. But it was pumping out, or it was processing over 3,000 gallons per minute. But these things can go, as you can see how small this, under a half gallon per minute. They can be very small, almost, I've seen ones the size of this, I guess, electrical box. So there's a lot of versatility with that, with the size range of this, and also because it's so small, and it can be put in discrete areas where, you know, maybe I've even seen instances where they're placed within doors, and also like just they're not a big eyesore compared to these large packing towers. So just as he went before, there's the science of it, but we've already touched on that. So when it comes down to size of the multi-sieve, the efficiency is changed kind of on 3 parameters. It's the number of trays, the airflow rate, and the duration that the multiple sieve air stripper is being used. So here I got 2 graphs I found off a website selling a wide variety for rent or for sale multiple sieve air strippers. And as you can see, this one here has only 4. All the parameters are the same for these 2 here, except the number of trays. This one has 5 trays, and this one only has 4 trays. So if you kind of look at these trends, the trends are similar, but as you go with more water flow rate, the efficient. So if we just one for comparison here, we have one at 500, or one right here at 500, at temperature of water of 70 degrees Fahrenheit. We're looking at a 97% efficiency. Now, if you look here at 500 gallons per minute at 70 degrees, we're seeing almost 100%. So when it comes down to this, you got to think of what you want, what is the efficiency you want to produce out of your system, and then that will then point you in the direction of what size and style stripper you need. So just a quick little look at these 2 compared to each other. As Keith touched on before, the water hardness is an issue when dealing with packing material because of the fouling and the mineralization of things going on the packing thing. So especially here in Pennsylvania, you got to think about it, because generally we have pretty hard water here, especially in State College. So with that in mind, packed air columns usually require a pre-treatment of the water coming in just to reduce that hardness. And also, he touched on before, the air blowers are required, more air is required for the packed, so that's going to actually require more horsepower in the end, so you got to think of energy costs on that as well.
Justin. All right, now that you guys have a good conceptual knowledge of how airstripping, in-situ airstripping in particular works. We're going to get some case studies. The first case study, if you haven't heard of it, is Hanford Site in Washington. If you haven't read too much about this, I know we covered it once in class, but it is a good read, not only for the nuclear waste there, but also for the TCE, etc., that we'll be talking more so about with airstripping. So just as a brief rundown, it was designed in the 1940s. It stored a bunch of nuclear waste when they were doing tests and whatnot during World War II, etc., into the 1950s. And there's a lot of decommissioned reactors. There's also some chemical waste, which we're going to be focusing more so on for the purposes of this presentation. So in the site, they're mainly using air strippers, sieve tray in particular, to remove TCE. So one of the cool things about this site, I'll get into more detail on in a couple of slides, is near the Columbia River. So making sure that the TCE didn't reach the groundwater was really important because sooner or later it would flow down gradient into the Columbia River. So that made airstripping a really good option overall. So they did use a low-profile air stripper, sieve tray method actually, when they went out doing this. So it's a pretty common method that we discussed earlier. All right, so as I alluded to earlier, why use airstripping at Hanford Site? But you want to make sure the TC and whatnot doesn't reach the groundwater, because if it does, it's going to flow down gradient into rivers. Going back to kind of the principles of flow nets and whatnot we talked about in Geosci 432 and EME 303 for a little bit. So what they ended up doing is they wanted to remove this TC from the saturated to the unsaturated zones. That's where airstripping came in. They did it mainly using air sparging, and then after that they were able to further remove the TC from the unsaturated soil via SVE. So I'm just giving you a better idea of what was going on. You see we have the zone of saturation right here. This is where the TC was. The goal was to get this into the capillary fringe and beta zone up into the unsaturated areas so that could be removed via SVE. And by doing that, it's not going to reach the Columbia River and cause a huge environmental disaster. So just kind of a quick recap, what does airstripping not do, at least in this case, is it does not remove TCE, etc., specifically from an unsaturated zone. It's just bringing it from the saturated zone up to the unsaturated zone. That's done by SVE, so that's a good distinction to draw to further your understanding of these. So when they were doing this, it was performed by the Army Corps of Engineers. Essentially, the in-situ airstripping was the most effective. They removed about 98% of SVE by 1997. This started in the early 90s, late 80s. It was a very big project. When you go into research, Hanford Site, it's a very large site. So it was essentially successful. And the cost, which we'll get into more later, is about $80 per cubic yard, which is pretty typical for this method. As a case two, a little bit closer to home, in the 1980s, there's a company-owned piece of land that was eventually purchased by Cintas Corporation. They found out that there was PCE on site, and it was 80 times greater than the allowable concentration of PCE in PA groundwater. Unlike Hanford Site, they use a little bit of a less common type of remediation. This was done in the early 2000s. By now, the concepts of air sparging, air stripping have been around for a few decades. So in this particular remediation project, they looked to optimize that. And part of the reason was the debated effectiveness of air stripping. So they decided, well, let's try a new method. And that new method was an ART integrated remediation system that's made by ART Technologies. It's really not too much different from what we already talked about. It just combines several methods. You have an air sparger that's going to volatilize your compounds. And then from there, you're going to go into air stripping, which is a packer element column. And then from there, it's going to further be removed by SVE. They found out that it actually has a pretty similar removal rates in terms of effectiveness. As we said before, air stripping can already reach 99% effectiveness for removing all the various chemicals within the ground. But what it did find is by combining all these systems into one, you could do it twice as fast, which will save money in the long run. So it's definitely something to think about as engineers entering the field one day.
Okay, so so there have been several instances of air stripping working pretty effectively. So we're going to talk about the one in Chester, New Jersey. The site had been used since the 1940s as a municipal refuse and a solid waste disposal landfill. And there are many recorded instances of people dumping dead animals, solid waste oils and chemicals and sewage sludge and all this really, really bad stuff, which probably contributed to the contaminant MTBE and TCE being found in the water. And the groundwater was also used as drinking water, so there's obviously some public safety and health issues. So this one is an example of the low-profile air stripper, also called like a seed tray system. So after detecting the MTBE and the TCE, an air stripper was installed in 1998. And so there are basically, oh, sorry. Okay, so basically there are two basic treatment systems. There's pre-treatment and post-treatment, and in pre-treatment, the extracted groundwater is passed through what's it called? Acid neutralization and water softening. And then in post-treatment, it's passed through the 4 shallow trays, and you can see they're 5 feet wide, 3.5 feet long, and 6.5 feet high. So after they're passed through these trays, they are polished through the GAC system, which is granular activated carbon, and this remediation has been going on since 1998, so it is ongoing. So it was pretty successful. The TCE was successfully removed, and the influent MTB concentration was originally measured to be 220 micrograms per liter, and 10 years, I think when they measured it was 10 years later, it was 14 micrograms per liter, indicating a 94% efficiency rate. So it was pretty successful. They weren't able to measure the effluent efficiency rate, so they estimated it was about around 61 to 67% efficiency. So the second example of air stripping working is in Rockaway Township in New Jersey. It's very close to the Chester, New Jersey site, so it had a lot of the same issues. They found TCE, PCE, DCE, and DIPE in the groundwater, and a lot of the residents had been complaining of strange tasting water and strange smelling water. So they were able to find out that it was the DIPE that was causing the strange taste. So they decided to originally install the GAC system, the granular activated carbon system, to try to remediate the problem, but they decided to go with the packed air stripper to further remediate the TCE and the PCE that the GAC couldn't address. So this one is an example of a packed air stripper. Actually, it's one of the first ones in the United States that was designed specifically for volatile organic compounds. So their 1982 system was the original system, and it was replaced in 1995 with a newer one because the DIPE and the MTBE the concentrations were so low. They replaced it, and they didn't design to remove it. So the 1995 system was designed basically to remove VOCs, and in 1997, unfortunately, there was a spill. The underground storage tank was accidentally spilled and released more MTBE into the groundwater. So the concentrations of MTBE were already pretty low. They were around 5 micrograms per liter. So it wasn't too hard to remediate the rest of it. So they fixed the system, and it was pretty adaptable, and they were able to successfully remediate all the MTBE. So these are basically the differences between the 1982 and the 1995 tower. They have a lot of the same specifications, but the removal efficiency for MTBE was actually higher for the 1982 tower because it was designed specifically for that purpose. Yeah, so they were basically pretty successful. In 1982, they removed about 95% of the MTBE. there were originally 50 to 60 micrograms per liter detected, and they reduced that to 10 micrograms per liter, and they eliminated all the taste and odor complaints that were going along with that. And then in 1995, when they were taking samples, in 47 out of the 69 samples, the concentration of MTBE was non-detect, meaning it was lower than 0.5 micrograms per liter. And you can see this spike there, that the spike indicates the spill of MTBE through that underground storage tank. So yeah, that's it.
All right, I'm going to finish the presentation off by talking about the cost and availability. So first, I'm going to talk about air sparging, and there's a few things that are going to drive the cost up or down. The first is surface area, which is the primary cost driver, so that affects how many air sparge points that are going to be placed on a site. And the second is the depth to contamination, so that kind of makes sense. I mean, the deeper you go down, the more money it's going to cost. So I think the group last week used a similar table. So for a small site that's easy, it's going to cost $64 per cubic yard. And for a difficult site, which I don't really understand this, but it's going to be $28 per cubic yard, which is actually lower in cost. And then for a large site that's easy, it's going to be $18 per cubic yard. And for a difficult, it's going to be $20 per cubic yard. And these are the other methods that we talked about. So first, bioslurping is going to cost $56 per gallon of recovered LNAPL. Directional wells, it's going to range from $20 to $75 per foot for the hydraulic drilling. And in addition to that, it's going to cost an additional $50 per foot for a medium-sized drilling rig for the PVC installation. Thermal treatment is going to cost $32 per cubic yard, depending on the number of wells required per unit area. And hydrofracturing is going to be between $1,000 and $1,500 based on the number of fractures created per day. Then availability. So air stripping was first used in the United States in the 1970s and was used in addition to bioremediation. Today, well-developed technology is used on hundreds of sites across the United States and is being used in other countries as well. And you can rent or buy complete operational systems across the United States. That's it.
It's good to be embedded in the truth.
I guess we might still. Does anyone have
All kinds of stuff going on. Any questions? No questions? So, you had in your title in situ stripping, and you did ultimately get to that, but you spent a long time talking about ex situ, right? What was your choice in doing that?
Well, they're used in conjunction with in situ methods often, so we figured we might as well cover the technology used for both, because they're used in conjunction.
You made a reasonable case for it. Yeah, so that's fine. What else? You talked about thermal methods as well. You stolen someone else's fire.
Yeah.
The group coming on Thursday.
Giving a sneak preview.
Oh, sneak preview, all right. No, I thought that was fine. Any other questions? Did anything come in on Facebook or WeChat that we should talk about? All right. You're off the hook. Great. So sign up sheet. The presenter should also maybe sign up.
Justin?
You didn't know.